Hello, welcome to BC Video 9.7b, Part 1, Maclaurin Polynomials. Okay, so I'm going to show you a formula now because that was kind of cumbersome what we just did before on the previous video. So this is for Maclaurin polynomials, which is near or centered at 0. So this is for evaluating some function of a number near 0. Okay, so we have our original polynomial of degree n. And remember, we're writing it in reverse order. So we're starting with the constant term plus a1x. The reason we do this is so that the subscript of the coefficient is the same as the exponent of the variable, a3x3, a4x4. And it does end there because we are talking a polynomial, a finite polynomial. The derivative, if you take the derivative of this function, well, that becomes 0, that becomes a1, that becomes 2a2x, that becomes 3a3x squared, that becomes 4 times a to the 4th. If you take the derivative again, this will become 0, this is 2a2, this will become 2 times 3 times a3 times x squared, x to the 1. This will be 3 times this quantity, which will be 12a to the 4th x squared. This will be 4 times this coefficient, which is 4 times 5a to the a5, and then x cubed. And then the very last one, you'll take your n minus 1, you'll multiply it by n and an, and then you'll subtract 1 from the exponent. Okay, and then the third derivative and the fourth, and so on. So what happens is, if you notice, if we let x equals 0, if we take all of these and we let all the x's be 0, notice all these terms will disappear except for the first one. So Pn of 0 is a0, which, by the way, could be called 0 factorial. If I take the first derivative and replace all the x's by 0, all these terms disappear. I'm left with a1. If I take the second derivative at 0, replace all these x's by 0, they're all gone. I'm left with 2 times a2, etc. Now what happens is, if you'll notice here, we get 3 times 2. The next one will be 4 times 3 times 2. Well, that's 2 factorial, that's 3 factorial, that's 4 factorial. So it turns out that our a0 is equal to our Pn of 0 divided by 0 factorial. Our a1, if I isolate it, is the derivative of Pn of 0 divided by 1 factorial. And then our a2 is the second derivative at 0 divided by 2 factorial, etc. So instead of p, we're going to call it f. So we have f of 0, f prime of 0, because 0 factorial and 1 factorial are both 1. F double prime of 0 is 2 factorial over 2 factorial, etc., etc., etc. Okay, same idea. A5 would be the fifth derivative at 0 over 5 factorial. A6 would be the sixth derivative of 0 over 6 factorial. So here's what it looks like. An nth degree Maclaurin's polynomial with p subscript n being the degree, is f of 0 plus f prime of 0 over 1 factorial plus f prime of 2 of 0 plus f double prime of 0 over 2 factorial, etc. And now we're going to use a table to do this, okay? And the table, the only thing the table is going to figure out for us is the numerator of the coefficient, because you're still going to have the denominator, which for the x cubed term is 3 factorial, for the x to the 4th term would be 4 factorial, and for the nth term would be n factorial. So we're going to approximate f of x by using a polynomial of degree n near 0. So here's an example. Find a Maclaurin's polynomial of degree 3 to approximate cosine of x near x equals 0. Okay, so here's how the table is going to work. You're going to start with 0, 1, 2, 3 because you want to go to degree 3. You're going to have your nth derivative at x. So your 0 with derivative means your original function cosine of x. Then it's the first derivative, second derivative, third derivative. Now what you'll notice, the derivative of cosine is negative sine, the derivative of negative sine is negative cos, the derivative of negative cosine is positive sine, and then it starts to repeat itself. Once you've got the functions for all of the derivatives, now at x, now you're going to do them at 0, and that's because we're doing this Maclaurin's, which is near 0. Cosine of 0 is 1, negative the sine of 0 is 0, negative the cosine of 0 is negative 1, the sine of 0 is 0. So what we have is that cosine of x near 0 is equal to f of 0 over 0 factorial times x to the 0 plus the first derivative at 0 over 1 factorial times x to the 1. Notice how the derivative matches the factorial matches the exponent of your variable. So when you're at x cubed, it's the third derivative at 0 over 3 factorial. And therefore, and we're only going to degree 3 because that's what they asked for. That is what we found in the table. The 0 with derivative, which is just f of 0, is 1. F prime of 0 is 0. The second derivative at 0 is negative 1. The third derivative at 0 is 0. So remember, all we're getting in the table is the numerators of the coefficients of each term. And then that's over 0 factorial x to the 0, 1 factorial x to the 1, over 2 factorial x squared. 0 factorial is 1. This whole thing becomes 0, so it's gone. So does this. And 2 factorial is 2. And we end up with an approximation of 1 minus x squared over 2. So now you could use that formula to actually approximate the value of the cosine of a number near 0. Remember, it has to be near 0. So for example, you could say the cosine of 0.03 using it is a third degree polynomial. It's just that the term that of degree 3 happens to be 0. That would be 1 minus, and then we'd plug in this number. And this would be a lot easier to do and try and figure this out on your own, which you would not be able to do. I know this is a TI-89, but just to show you the graphs, this is the graph of y equals cosine x. And if we graph this function, here it is, 1 minus x squared over 2. And you'll notice that near x equals 0, it's hard to tell the difference between those two graphs. Okay?